awkward. The only thing in the learning modules is, just so you know, all this stuff is in module 6. Sorry, chapter 6. Yeah, the one class where I'm actually using chapters. Shearing stresses in beams and thin-walled members. You can see there's also a homework assignment in there that I think I created it, I don't know, last week sometime. All right, let's go here. What I want to talk about is shearing stress. And if you look at this diagram on the right, it shows a stack of thin plates forming a larger plate, right? And that's similar to how something like wood, right? Wood has a grain structure, right? Wood is anisotropic, so it's got two directions that are similar, and the one direction is different, right? Like cutting across the grain. You either cut in line with the grain or across the grain. And shearing stress, remember back from, I think it was chapter 3, shearing is where two surfaces are sliding over each other, right? You're shearing, so they're sliding. And pure bending does not involve shearing, but real bending can have shearing. And that's demonstrated over here, right? If I were to apply a force on the top of this stack of beams, right? Well, what's happening? You can see that they're sliding past each other, right? Because the ends are no longer, like the end of this one is not in line with the end of this one. It's not in line with the end of this one and this one, right? So they've slid over each other. This is shearing under a transverse load, right? And you can see that demonstrated with we've got a piece of wood in here, a timber beam, I guess. And it's loaded transversely, right? In other words, now I can't tell if this was being weighted down or this was being pushed up. It's likely you have this, and then you've got some kind of weight in this center area that's being loaded up. But this is basically a it's a transverse load that's causing shear, right? Now, if with these beams, if I had taken and welded an end cap on, right, and fixed all these beams so that their ends could not slide away or past each other, right, I would get a scenario like situation C, where I would get pure bending, right? So this is pure bending, and this is a transverse load causing shear. So we're going to look at shear now, and transverse loads. Oh, good, I'm recording. This is a very busy slide, and I wasn't sure how much to cover, but I want to point out some notation here. It's really kind of hard to see. There's a little tiny area. Right, off this area, they've got an arrow pointing outwards. This is the normal stress, right? Sigma x. In line with that, we've got some arrows, and those have subscripts to them, tau xy and tau xz. You can kind of see the subscripts over here on this bigger one, tau xy. I don't like the way they did this because the arrows are pointing in the direction that are not correct. But this designation is the first letter represents the plane, or you're on this plane, and the first letter represents the perpendicular axis, right? So this is the face whose perpendicular axis is the x-axis. The second letter is the direction of shear, right? So, or it tells you the orientation of that plane. So the plane is the x-facing plane, right? Where shear is in the y direction. And that's why I like this arrow better, because this is consistent with positive, right? This area, right? The normal axis is x, and this is the y shear direction, right? This is tau xz. This would be a z shear direction, right? So depending on the situation, right, you can have a xy, you're gonna have xz, you're gonna have both, right? We'll get into scenarios like that. But every face of an element in a beam or in a material, right, you can break it down. You can talk about the shear stress, tau xy, right? So this would be the shear stress in the y direction on the plane with an x perpendicular axis. That makes any sense. So this plane is perpendicular to the x-axis, and the shear force is in the y direction. Now in this case, it's a negative y direction. So that's the notation that they use for shear. It's a tau with two subscripts, and the first subscript tells you the axis that plane is perpendicular to. The second subscript tells you the direction of the shear force, right? So keeping that in mind, you can write a bunch of things down. Again, for this little element here, we could say that the force on this element is basically, or the force on this face, right, is the integral of all the dAs, right, all the little areas, times the sigma x, the normal stress, right? That's the total force. Remember, normal stress is a force per unit area, dA, right? All we're saying is we got a bunch of little incremental areas. Same thing for the y direction, right? Except now, what we have with the y is the force in the y direction across this face, right, is this shear stress tau xy. So the plane that has a axis, that's perpendicular to the x-axis, and the force is in the y direction, dA, right? This is basically minus v. This is that transverse loading, this v here. This is that internal shear stress that we were working on in the previous chapter of determining where that was, right? And in the chapter, we figured out that internal shear stress. Now we're looking at, okay, well, we can actually write that as an integral of all the shears on all the little areas, right, in the y direction. And similarly for the z direction, you can write, again, all the shears dA, tau xz, and this is 0. Now, again, for this particular case, you have a beam that's, being bent. It's got a bending moment and it's got some load. So for this is true for this scenario, right? The force x is 0, force z is 0, force y is negative v. Similar for the bending moment, right? You're gonna have a bending moment about x, so about this direction, but you can write that bending moment with respect to the different shear stresses, right? So tau xz, right? That's the plane that's perpendicular to the x-axis, right? And it's got a shear stress in the z direction, right? So y is the location of that. Y times that tau minus z times the other tau xy, right? Times the integral dA gives you the moment. In this case, it happens to be 0. The moment about y, right? This is the only, moment about y is again going to be sigma x times z, right? The distance away from the y-axis, because now we're taking a moment about y, and that's going to be equal to 0. Again, in both these scenarios, you see, especially for this one, you can see it's symmetric about y anyway. And then for m of z, moment of z, this is the only one that has anything. It's negative y sigma x. So whatever sigma x is, right? The force that way, and that's your moment. And negative y is just again relative to the direction or the dimension 0 to y, the position that you're on. This is a negative function to begin with. Remember, because tension and compression, well, you don't know where the neutral axis is on this thing. So it's gonna, you have to take into account the fact that you're working from, in this case, 0. Let's see. Another point of this, if you exert shear stresses on a vertical face of an element, you have to have a stress exerted on the horizontal face, right? Because if you're shearing downward, you've got another shear in the horizontal face to keep things in balance. Longitudinal shearing stresses. Those are basically stresses that run along the length of the beam. They also exist in a beam subjected to these transverse loading. So shear, again, longitudinal stresses. Let's get into some little more details. That's less theory, more looking at examples. If you look at this beam here, right, it's a simply supported beam between A and B, and this is its cross section. It looks like this trapezoid. It's subjected to a bunch of different things. You've got some concentrated loads, some distributed loads, and we're looking here at this location C, which happens to be a certain distance x from one end. Right, we already figured out back in the previous chapter how to figure out the shear and bending moment, internal shear and bending moment of a beam at that location, right? Now we're going to look inside and we're going to say, okay, what's happening to a specific volume, like a very tiny volume, a finite volume of that beam? And in this case, we're taking just this top location here. We're looking at the shaded, the darker shaded area. Notice it's got C and C prime, D and D prime. This will tell you the C and D are at the surface. The C prime and D prime are in the body. And then you've got a little increment delta X, right? And that's denoting this. You've taken a small slice of this beam left and right. It is really hard to see these letters. I'm even having trouble seeing them. I probably should have broken up this slide. This height from the neutral axis, so notice this is the neutral axis of this trapezoid. From the neutral axis, you have a height C, which takes you all the way up to the top surface. But you also have this height, what is this, Y1? I think it's Y1. Yeah, I should have blown that up for my old eyes. Y1. That's the height at the bottom of this this little portion that you're looking at is above the neutral axis. And we got this little area A. So let's go through some of these formulas. First of all, so then we're gonna break this down, and you can see that remember your forces change with depth, right? Remember, your normal force is highest at C, right? As you go closer to the neutral axis, your normal stress, not your normal force, your normal stress decreases, right? And that's what's shown by this drawing here. It's going to go to 0 at the neutral axis. So these stresses on both sides, this element itself has, it's got the weight on it, it's got the normal stresses on either side, right? It's got the shears, VD prime and VC prime, and it's got this delta H. Delta H is along the bottom of this element, right? Because we're taking an element that's you know, it's not, it doesn't have its bottom at the neutral axis. So there's got to be some kind of sort of longitudinal stress, right, denoted by delta H. And we can write that out by doing a force balance. So we can look at this and say the sum of the forces in X is equal to 0. Well, I've got delta H, right? And then I've got sigma D minus sigma C dA. What's that? This is the sum of the stresses, right? The normal stresses over these areas. So normal stress times area gives you a force, right? That's the total force acting on this face on the D side. And then the total area acting on this face on the C side is denoted by sigma C, right? You're just taking the difference of them. Sigma D is acting one direction, sigma C is the other direction. And you take the integral with respect to area. And you wind up with basically a moment, right? You can factor out, let's see, delta H is going to be md minus mc over I integral y, right? This, this comes from the equation, which we don't have in front of us. Well, remember, the bending moment times y divided by the moment of inertia, right, gives you sigma, right? Sigma at any given location is just bending moment times y divided by I, right? That's how we wind up pulling all this stuff out, because all this stuff is constant, right? The moment of inertia of the cross section is constant. The bending moment is constant. The only thing that changes with area is y, right? And that's what causes sigma to change. Let's see. Q. We're introducing a new variable here, Q. Q is the first moment with respect to the neutral axis of the shaded portion. So here you've got a shaded portion, right? And Q is the first moment of that portion. So it's y dA, right? It's the integral of y dA, whatever all the little areas are in that portion. And what is y? Y is just that distance between this shaded portion and the neutral axis. Let's see, so now we can write this out. md minus mc is just dm dx dx, right, which is equal to v dx. You can substitute in your delta H. You wind up with delta H is VQ over I dx. This is what's called, well, and then you divide through by delta X, and you wind up with this, this Q, this little Q. This Q is called shear flow. And it's not really, I mean, it's not really, there's nothing flowing, right? But it's the way the shear stress goes, right? It's a shear stress per unit length. It's a horizontal shear per unit length of the material. That's basically your transverse shear, right? Times your Q, your first moment of that area, divided by the moment of inertia of the cross section of the beam. That's a much better graphic. It's from the bottom up. You could do the same analysis using the bottom portion of the trapezoid. Notice they've labeled this A prime, this area prime. Now we're at C prime and D prime, and then C double prime and D double prime. So we're just looking at the cross-sectional area. You basically can do the same analysis we just did on the previous slide and find, all right, the first moment is this, y dA, right? I is this, y squared dA from A to A prime, right? And you can wind up with the same result for the lower area. Notice it's a negative Q, right? VQ over I. But this is the first moment with respect to the neutral axis. That's what that Q is. Let's try to do this in an example, because it makes more sense than trying to explain it through the oops, page here. Oh, go back to that. We have a beam, and it's made of 3 planks. Oh, this is an in PowerPoint example, isn't it? Yes, this is in the PowerPoint. It's made of 3 planks, and they're all nailed together, right? One nail up here, one nail up down here. The spacing between the nails is 25 millimeters. So this spacing is in and out of the page, right? This beam is coming out of the page towards you and going into the page away from you. Right? You're looking at a cross section, and there's nails every 25 millimeters if you go into the page or come out of the page, right? So you know that, and you also know the vertical shear in the beam is 500 newtons. So in this cross section, in this beam, it's 500 newton vertical shear. Now we want to determine the shear force in each nail. So remember, that vertical shear is causing longitudinal shear, right? Along this beam, it's causing this top portion to want to slide along this vertical portion, right? And the nails are holding it in place. The nails are the ones that have to resist that longitudinal shear force, right? The shear force that's basically acting in and out of the page. This is so much more difficult over Zoom. Show you my hands and how things are moving. And we want to know the horizontal force per unit length. Oh, we can find that first. And then once we know the horizontal force per unit length or the shear flow, right, then we can figure out what the shear force is in each nail. So let's look at the solution here. Again, this is not a really detailed problem, so I just left it in the PowerPoints. But our area of interest is this up here, this shaded region with a centroid C prime. What we're going to be doing is we're going to find what's the horizontal force per unit length, right? That little Q on the lower surface of this top plank, right? So we have to take this area, and we're going to do a moment calculation for it. It's basically the area times the y bar. Y bar is the distance of this area's centroid from the neutral axis. See, that's where that 0.06 meters comes from. So we've got the area, 0.02 times 0.1 meters, times that distance. So all we're doing here is this moment, right, of that area about the neutral axis is 120 times 10 to the minus 6 meters cubed. Now we look at the total moment of inertia for the entire beam cross section, right? This is again, all these terms should be recognizable. These are rectangular terms, right? 1/12 base times height. This one right here, we've got the 0.020 times the height of 0.1. That's this tall middle one, right? Cubed. So this one is the tall middle one. Then we've got 1/12 times, we got 0.1 times the 0.02 cubed, right? So that's each of these top and bottom sections. They both have the same moment of inertia about their centroids, right? The 0.1 meters times the base cubed divided by 12. There's 2 of them, so we add that in. And there's an offset with the neutral axis, which is, let's see, the 0.02 times the 0.1 meters times the 0.06 meters squared. So 0.06 being the distance between one centroid to the other. Remember the d squared term? It looks like, oh yeah, see this bracket here? This is showing that they're both 2 times, right? 2 times each of these. It doesn't matter if they're on top or the bottom for the overall moment of inertia, right? They're identical. So the distance between the centroids and the y-axis or the neutral axis is the same, and you're squaring it, so it doesn't matter if it's positive or negative. So you get a moment of inertia of 16.2 times 10 to the minus 6 meters to the 4th. we're finding the shear flow. The shear flow is that force per unit length, right? We've got, oh yeah, we've got our 500 Newton shear, right? We've got our Q, which we calculated over here, our moment for just the top portion, right? And then the moment of inertia for the entire cross section of the beam. And we get 3,700 Newtons per meter, right? This is telling us that that's the force per unit length between this top beam and this bottom or this middle beam, or it works both ways, this middle beam and this bottom beam. It's that force per unit length that's being trying to separate them, trying to cause them to slip over one another. So this is what the nails have to resist. This is per meter. Now, the nails have a spacing of 25 millimeters, right? So for every 25 millimeters of distance, you've got one nail working. Now you can look at this a few ways. You can look at it as the nails in the middle. Let me get a piece of scrap paper here. Right, if I'm looking at the top of this beam, I'm basically looking down at something like this, and I've got a nail, right? I've got another nail, and I've got another nail, and another nail, and so on and so forth, right? This is 25 millimeters, right? But that's also the same as saying, well, the distance between directly in the middle of each is 25 millimeters, right? So for a given meter, or for a given length, we've got, what did we say it was? It was 3,700 Newtons per meter, 3,704 Newtons per meter, right? We're just dividing that up by the fact that we have these nails every 25 millimeters, right? So we're going to multiply that by 0.025 meters, right? 3,704 Newtons per meter times 0.025 meters. That's the spacing. This is how much one nail covers in distance. And you get a force of 92.6 Newtons. So that's the force that a nail has to resist. Now, let's relate this to earlier material, right? Earlier material, we had a cross section. What do we got? 92.6. You know, if we have a nail is basically a cylinder, and it's running through this object, and it's got a force on it, a shear force. What do we say? 92.6 Newtons. Right? So the area for shear is the cross section of the nail. So remember, that's just force over area gives you the shear stress in that nail, right? So depending on what you're doing here, now you're saying, okay, maybe I want to size my nails. Given this force, I want my internal shear stress in the nail to stay below a certain value, right? What's the area of that nail need to be, right? So now I can choose what size nail to get. This is not in the chapter. This is just relating back to, you know, previous stuff, right? You can then design and specify what size nail do you need to make sure that that doesn't slide. Oh, okay, 2 slides before we get to, all right. So let's go back now to looking at the cross section of a beam, and we're going to talk about shearing stresses. We're going to talk about average shearing stresses, but we're also going to look in and take a look at the incremental areas here. But the average shearing stress, right, on a horizontal face is you basically take the shearing force, delta H, on the element and divide it by the area, right? So we've got the average shearing force or shear stress is delta H divided by the area, right? And that gives you this, remember delta H is Q delta X. Delta H is that force, right? And Q is that force per unit length. So that's force per unit length times unit length divided by area. And you can replace this stuff by, let's see, we've got VQ over I, and we got delta X over T delta X. This T is the thickness, right? Thickness delta X. That's your area for shear. Notice delta A is on top here, right? It's thickness times delta X. That's your area. And this gives you an average shear stress of, again, the shear times Q divided by I over T, right? The moments of the area, the moment of inertia, and then the thickness T. So the other thing to pay attention to is on the top surface of a beam. When you put a beam under bending, right, your top and bottom surfaces, your surfaces that are furthest away from the neutral axis, they see the highest normal stress, but they see zero shear stress, right? Because they are the top, they are the outside surfaces of that beam, right? There's no shear stress on those surfaces up here, right? So tau yx and tau xy down, well, xy up here and xy down there. So tau yx, right, that's the area that's perpendicular to the y-axis, and the shear force is in the x direction. This one is a little more, you have to sort of squint to see it. This is right on the incremental upper and lower edges, right? Right at the start. So it's a very, very tiny area, remember. And then one assumption here is, long as the width of the beam cross-section remains small compared to the depth. So depth being, you know, basically the length of the beam, right? As long as the width is small compared to its depth, the shearing stress only varies slightly along the line. Let's see, D prime 1, D prime 2, D prime 1, D prime 2, which is apparently this. Oh, this one right here, D1, this one. There's very low variation. Let me, oh, there's, oh, I guess they took that out. You can see these much better in your textbook. Again, I probably should break this slide up into multiple slides showing the pictures blown up a little bit. Let's look at a very simple rectangular cross section now. We've got this beam, looking at the cross section, and this is what the shear force looks like. And let's go through this. We've got tau xy is VQ over IB. Well, Q is based on this area here, right? The shaded area. So for a given area, you've got your centroid, right? Minus your y, well, centroid squared minus y squared. This is what it turns out to be. The 1/2 c squared minus y squared is your Q. Your I is your moment of inertia of your entire object, right? Which is just b squared, let's see, base times c cubed, right? Or height cubed. Yeah, again, this is one of those things where there's more steps involved in between here. You're going to replace IB with A 2/3 BC cubed, right? Because the total moment of inertia of the beam is B times 2c cubed, right? And you wind up with, once you cancel out the c's from above, you wind up with this term here, 3/4 c squared plus y squared BC cubed. Oh, that should be a negative. Oh, anyway, I got to repair that slide. Anyway, the point is you wind up with after the analysis, you do the analysis, you wind up with this equation for tau xy. 3v over 2a times the quantity 1 minus y squared over c squared, right? So what is it? Let's look at the trend of this thing. This tells you that for any distance you are from the neutral axis, right? Once you hit the distance c, it doesn't matter, minus c or plus c, it's c squared, right? 1 minus c squared over c squared is 0, right? 1 minus 1 is 0. This whole term goes to 0. That tells you your maximum shear, or sorry, your shear at the top and bottom faces is 0. However, as your y decreases, right, as you get closer to the neutral axis, you wind up becoming, this term becomes smaller and smaller and smaller. So you approach, right, at y equals 0, tau max is 3/2 v over a, right, which is just your shear divided by your area, 3/2. These become a little more intuitive as you do example problems, but I want to show you the American standard wide flange beam, right? Notice the shape of this beam. It's got a very wide thickness up here, right? It's got a lot of area. So as you move down, right, you've got a lot of area up here. So your area down below, this is a bigger number, right, for a given section of the beam. 3/2 v over a. While your v is constant, your a is pretty big up here. So 1 minus y squared over c squared, right? Depending on where your y squared is, up here again, it's going to be far away, it's going to be close to c. This becomes a very small number, right? Obviously, the top is 0. But this is what the trend looks like in the top portion of the beam, right? Very low longitudinal stress. Once you hit this center section, notice the thickness drops a lot. And that small thickness affects the area, right? That area gets a lot smaller, right? So the shear stress gets a lot bigger. So you wind up with a shear stress that's actually fairly uniform over the height of this center section of the I-beam. So when you design these flange beams, or when they're looking at internal stresses, they can be pretty confident that the max shear is going to be distributed. You know, it's whatever the max shear is, it's pretty much equivalent throughout the entire height of that web, right? That thickness of that beam. And they give you the generic formulas for them, right? The average shear stress is VQ over IT. The maximum shear stress is V over the area of just the web, right? And you can see that came right from, well, yeah. Let's look at the sample problem. Sample problem 6.1. We've got a beam, AB. It's made of 3 plates glued together. It's subjected in the plane of symmetry. So be careful when you're reading these problems. This beam, if you look at the cross section, right? This is running in and out of the page. And then over here, we can see this going left to right, right? These loads are they're told in its plane of symmetry, right? So its plane of symmetry is this plane right through the center of it, right? So these loads are basically applied right down the center of this beam, right? Not off to the side. That's all they're telling you there. And then it tells you knowing the width of each glued joint is 20 millimeters. Now, be careful, right? Width, in this case, that's the height, 20 millimeters, because they're obviously different different lengths here. If you know, I would normally think of this as width, but their bases are different, right? This is a 60 millimeter, this is 100 millimeter. Determine the average shearing stress in each joint at section NN of the beam. So let's look over here. Section NN of the beam. The location of the centroid is given in figure 1. There's the centroid. So they actually calculated the centroid for you. Very nice of them to do. 68.3 millimeters from the bottom. And the centroid moment of inertia is 8.63 times 10 to the minus 6th. So this is the moment of inertia of the beam. And we have to determine what? What do we have to determine? Doesn't actually tell you. Oh, here it is. Yeah, determine the average shearing stress in each joint at sections NN. So each joint, right? You've got a joint here and a joint here. Joint A and joint B. It's much clearer on the, the other format. So now let's look at this problem. And I'm going to start solving this. I don't think I'm going to get through it all, but we'll see how far we get. We can at least do the force balance. And I'm going to draw this right up here. I'll draw the beam. I'll sketch the beam. A and B, right? And then right in the middle, we've got this, we've got 1.5. This is what, kilonewtons. We got 0.4. We do know that this is symmetric. From symmetry, A equals B, right? So sum of the forces in Y equals 0. We've got, I'll just use A, 2A minus 3 kilonewtons. A equals B equals 1.5 kilonewtons up, right? Fairly straightforward. Something you probably could have just looked at and figured out. Let's look now at what's happening at section NN. So I'm going to draw the free body diagram of beam left of NN. So here's NN. I'm going to take this this down here. I'm going to draw a free body diagram of that. Oh, what time is it? .5 kilonewtons. I've got V, and I've got M. So this is only that left section of the beam, right? We're going to figure out what the shear and bending moment are. In fact, really all we need is shear here, right? Because that's what we use in our equations for the shear force. For the longitudinal, we just need V. So find V at this location. And this is nice because it, any concentrated load, between any concentrated loads, it's constant. So we don't need to worry about, distance from a point or whatever. Sum of the forces in Y equals 0. We've got 1.5 minus V equals 0. So V is equal to 1.5 kilonewtons. Again, all very basic statics balances so far. So that's our shear force. Now what I think I'm going to do here, let me. Right, we're going to use, oops. We're going to use this equation here. The average shear stress, VQ over IT. And we need to know Q, which is area times Y bar. And we were given the moment of inertia and we're given the thickness, and I think that's all. Average shearing stress, so tau average is VQ over IT. So from this, I'm going to first examine joint A. It's 149. You know what? Let me just write out the first moment of area. It's area times Y bar, right? And what do we have? Well, for joint A up here, I guess it's a lowercase a, the Q of interest is this area up here, right? This is the first moment of area. Let's see, the first moment of area above the neutral axis. And because we're looking at we want the shear at this joint, right? We're looking at the area above it, right? That's what this Q is. So Q is just going to equal, what do we have? We have 20 times 100. I should have just done this in meters. Y bar. Y bar is from the centroid here to this centroid. This is going to be, let's see, what do we got? I've got 80 plus 40 minus 68.3. You got 51.7 minus 10, 41.7. This is 41.7. Because remember, the centroid is in the middle here, right? So you're 10 down from the top. So I've got 41.7 millimeters. This is converting 1 meter to millimeters. Gives us a Q, or from millimeters to meters, 83.4 times 10 to the minus 6th meters cubed. All right, let's stop here, and we'll pick up with this on Wednesday. But this is the first moment of the area of just this top area, right? So think about it this way. This area has a moment, right, about the neutral axis that contributes to the fact that the shear, right, between this and the area below it. That's kind of what we're doing here, right? We're taking a relative moment and comparing them. All right, so let me stop the recording. And are there any